Yeah. Let us start. One more session.
Morning we discussed how to design, how to we saw the details of coagulation. Morning. Okay. Then we also discussed about Clariflocculator, physical how it appear and all we saw. Now let us see the design calculations of Clariflocculator. So, as we discussed earlier, Clariflocculator consists of 3 units. So one is rapid mixing unit, the second one is flocculator, third one is sedimentation tanks. All these 3 things together known as Clariflocculator. So Clariflocculator consists one, two flocculator, 3 sedimentation tanks. So morning we discussed about this. So let us see one by one. Let us see first design of rapid mixing unit. Purpose we wrote already. Rapid mixing unit is used for blending the chemical coagulant in water, mixing chemical coagulant uniformly in water. So when it is uniformly mixed, then every colloidal particle get intimate contact with the rapid mixing unit is used for blending the chemical coagulant in water, mixing chemical coagulant uniformly in water. So when it is uniformly mixed, then every colloidal particle contact with the So rapid mixing unit is a square or circular tank. It is a square or circular tank equipped with a mechanical mixing device. Already I wrote in the morning session we discussed how to design this. So design of rapid mixing unit is based on 2 parameters. One is detention time, the other one is velocity gradient. These 2 parameters influences the design of rapid mixing unit. Detention time DTRT. So normally we provide a detention time of 1 to 3 minutes in rapid mixing unit. So generally a detention time of 1 to 3 minutes is provided. So once you know detention time, what can you find out? Volume of rapid mixing unit is equal to Q into detention time. We mentioned that is a square tank. So normally we assume depth. So depth is assumed as anywhere between 1 meter to 1.5 meter. So using this, what I can find out? Surface area or plan area of rapid mixing unit. So surface area of rapid mixing unit is equal to, it is volume by depth. So I'll take it as surface area. So for square type mixing basin, this is square type. So dimensions are B into B. For square type tank, surface area is equal to B into B. For circular tanks, surface area is taken as pi by 4 d square, where d is equal to diameter. This is d. Understood? This dimension is taken as d. That's all. Nothing is there in the design. In addition to that, second parameter is velocity gradient. Velocity gradient is the measure of degree of mixing. So when you design this rapid mixing unit, we design in such a way that it has to produce a velocity gradient anywhere between 700 to 1000 second inverse. It is denoted by G. For uniform mixing, it has to generate a velocity gradient G anywhere between 700 to 1000 second inverse. Okay, the unit of G is second inverse. 1 by second. This is. So this G value we will calculate by using equation G is equal to root of P by V mu. So it is a measure of degree of mixing. Degree of mixing in turn depends on turbulence it generates. Turbulence it generates depends on speed with which we operate the shaft. So in this equation, P is equal to power in watts and V is equal to volume of rapid mixing unit in meter cube. Okay, mu is equal to coefficient of dynamic viscosity or absolute viscosity. The units are Newton second per meter square. So if you substitute them in this unit system, this is in meter cube, this is in watts, then you will get G value in which unit system? 1 by second. Then G unit is 1 by second. We write it as second inverse. Okay. So what I mean to say is, so when you have a shaft, when you rotate the shaft inside the water, there is a shaft. There is a blade. This is a blade of a shaft. This is a shaft driven by motor. So this is driven by motor. This is motor. So also RPM. So if you know the 10 value, in so and so RPM it rotate, then what it produces inside the tank, this is. Inside the tank water is there. So this will be rotating inside the tank. Okay. So once it rotates inside the tank, what happens? It induces velocity gradient. Velocity gradient means what? So fluid, the molecules, water molecules move inside this with a different speed. So if you draw the velocity profile, so velocity is maximum at the periphery. As you go towards the shaft, velocity keep on decreases like this. The slope of this one is called velocity gradient. So G is nothing but velocity gradient, nothing but slope of this velocity profile. So fluid elements move with different speeds. So which are close to shaft, they move with a different speed. This is one fluid element, this is another fluid element, this is another fluid element. This move with the speed V1, this move with the speed V2, this move with the speed V3. This is at a distance R1 from the center of the shaft. This is at a distance R2 from the center of the shaft. This is at a distance R3 from the center of the shaft. So omega into R is equal to velocity. So this move with V1 speed, this move with V2 speed, this move with V3 speed. This is at a distance R1 from the center of the shaft. This is a shaft rotating inside. This is at a distance R2. This is at a distance R3. So V is equal to omega into R. Right? What is omega? Omega is equal to angular speed. Omega is equal to angular motion, angular speed, which is equal to 2 pi n by 60. So if you know speed with which the shaft rotates, you can find out omega, angular velocity. It is rotate with n rpm. So one time it rotate, 2 pi radians it cover. N times it rotate, 2 pi n radians it cover. This radians per minute convert into seconds 1 by 60. So V is equal to omega into n. V is equal to omega into R. Angular velocity into radial distance is equal to linear velocity. So as R increases, V also increases. So from the center of the shaft, if you go away, so velocity keep on changes. The slope of that velocity profile is called velocity gradient. So V we got. Then power is equal to, power P is equal to this force into velocity. What is that force? Drag force. So power is equal to, drag force is CdA rho W into V square by 2 into V. Therefore power is equal to this CD into A into rho W into V cube by 2. Where CD is equal to coefficient of drag or drag coefficient. A is equal to projected area of blade. It is projected area of blade. Rho W, density of water, V is equal to, so it is velocity of fluid elements, V. So that power, whatever, that is okay, you can take here, V value. This R you can take here, this is. From the center of the shaft, this is R. So here V we can calculate at the tip of this one. So V is equal to omega into R is equal to this. So we can, using this equation, we can work out power. Power we get in which unit system? Watts. So we will get power in watts. CdA rho V cube by 2. So that's how we can work out this. But this much depth you don't go. Generally whenever G is given, P is unknown, P is given, G is unknown. So volume you can work out by using detention time. So that is how you can frame questions in the exam. Okay. So two things you have to remember related to rapid mixing unit. One is how to work out volume. So volume is equal to, it is Q into detention time. And once volume is known, then we can fix up surface dimensions of this tank. Then with the help of this, we can find out, right? Using G is equal to root of P by V mu, you can find out whatever you require. So power, volume or something like that. So both of them are interlinked with each other. So whenever you are expected to work out G, power is known component. Whenever you are expected to find out power, G is a known component. Understood? Let us try one gate question. This is a gate question asked in GATE exam. The question is like this. A water treatment plant is required to process 28,800 meter cube per day of raw water. In brackets he has given density 1000 kilogram per meter cube, kinematic viscosity 10 power minus 6 meter square per second is given in brackets. The rapid mixing unit I can type them and then give you, but I don't have any person to type. That's why I'm writing. So kindly excuse me for wasting your time. But anyway, the rapid mixing tank imparts a velocity gradient. And second inverse to blend 35 milligram per liter of alum for a detention time of 2 minutes. Alum with the flow for a detention time of 2 minutes.
Okay.
Find the power input required for rapid mixing is, of course, he has given options. So I'll frame this into two parts. Find first surface dimensions of mixing basin. If depth is 1 meter, 2 power input in watts required for mixing.
Come on, work out. Follow that procedure which I gave you. Comfortably you can work out. Solution.
So what is given to you? Q is given. 28,800 meter cube per day. Density of water is given as 1000 kilogram per meter cube. Kinematic viscosity is given 10 power minus 6 meter square per second. Then what else is given? G value is given. It is 900 second inverse. And alum dose is given. $35 milligram per liter. Then I will ask you to two things. And depth of tank is given as 1 meter. So surface dimensions of a rapid mixing unit, dimensions of a square type rapid mixing unit. I'll put that wording also, so that there is no ambiguity with you. Because some people assume it as circular also, because you competitive exam, so crystal clear clarity, they will frame questions. Dimensions of a square type mixing basin if depth is equal to 1 meter. Okay. So first one, we got to work out surface dimensions. And second one, power. So let us see. So volume of rapid mixing unit is given as, you can work out. Q into detention time. So detention time is given in the question 2 minutes. This is also given in the question. So V is equal to 28,800 meter cube per day. This I am converting into seconds by 24 into 60 into 2. So this is in meter cube per minute. This is in minutes. So therefore what happens? Meter cube, minute get cancelled, you left with meter cube. So straight will get answer in meter cube. Now how much it is? Meter cube per day. To convert into meter cube per minute, divide by 24 and 60. 24 by 60. 28,800 by 24 into 60 into 2. So it is 40 meter cube. So depth is given as 1 meter. Surface dimensions is equal to volume by depth. 40 by 1 is 40 meters square. Since it is square type, surface area is equal to B into B, which is equal to 40. That implies B is equal to root 40. So we have to provide 6.32 meters. So provide the square tank of size 6.32 meters by 6.32 meters as a rapid mixing unit. That was the answer for first part. Surface dimension means 6.32 meters by 6.32 meters. Second part, power. So to find out power indirectly, but we require dynamic viscosity. So kinematic viscosity is equal to dynamic viscosity by rho W. So mu you can replace with the kinematic viscosity also, mu into rho W. So I can also write this equation as P by V into mu into rho W under root. Still you will get answer in 1 by second. Okay? So 900 second inverse is equal to P by V, we got 40. Kinematic viscosity is given as 10 power minus 6. Rho W is given as 1000. So the unknown is P. Therefore P is equal to. From this you can find out. So 900 it is into 40 into 10 minus 6 into 1000. So it is power is 32,400 watts. So that is how we can work out. A part of the question only will get in the exam, not complete question. Okay? That way we are lucky. Pratik, definitely I will cover that part, air requirements, methane consumption. Definitely need not worry. Pratik, Okay. Next, let us try one more question. This question has been asked in ESE exam. A flash mixer of 2 meter cube. Flash mixture means it is also rapid mixing unit.
With the velocity
Gradient of mixing mechanism equal to 600 second inverse and fluid absolute viscosity. One into 10 power minus 3 Newton second per meter square is continuously operated. What is power input? Per unit volume.
Why not?
He has given options, but I am not writing options there. Now work out power you have to find out. What is unknown? Power. What is given? V is given. V is 2 meter cube and G is given as 600 second inverse and mu is given as 1 into 10 power minus 3 Newton second per meter. Just formula substitution, nothing is there in this. Come on. So G is equal to root of P by V mu. So 9 and sorry, here G is given as 600. So find out power. Come on, work out. You can ask doubts straight away, Pratik, no problem. Telegram channel create karo sir, definitely. I'll create one Telegram channel. Sure, Pratik. I am new to this platform, but I'll try to Telegram channel. You can create channel on our own. Is it so?
Okay.
What is power? Come on, calculate. So 600 square into 2 into 10 minus 3. So it is 720 watts. So this is how we can work out. Okay, let us see second part, that is flocculator. Flock, it is a rectangular tank provided with the paddle rotors. Okay. So design is based on same. Moreover, detention time, but values are different. Concept is same. Second one is velocity gradient. Values sometimes you are forced to remember. Normally a detention time of 20 to 40 minutes, 30 to 40 minutes, 20 to 40 minutes we provide. A detention time of 20 to 40 minutes is required to produce good flock in water.
So 20 to 40 minutes
You can provide. So using detention time, what you can work out? Volume of the mixing basin, volume of the flocculator. Therefore, so volume of the flocculator is equal to Q into detention time. Normally depth of flocculator we provide. Assume depth of flocculator H value anywhere between 1.5 meters to 3.5 meters. You can fix surface area. Then surface area of flocculator. It is volume by depth. So surface area of flocculator is L into B. So using L is to B ratio, you can find out length of the flocculator and width of the flocculator. That is how we design. Okay. Once we know dimensions, then we cross check with velocity gradient. The velocity gradient of ranging from 20 to 80 second inverse produce good flock in water. So values are different. There it is 700 to 1000 second inverse. Here it is only 20 to 80. There detention time is 1 to 3 minutes. Here detention time is 20 to 40 minutes. This is the differences you are supposed to notice. Okay. And here the point here is the size of the flock produced in water that neither dependent on velocity gradient nor dependent on detention time. It depends both of them. The size and the mass of flock produced in water depends on unitless number GT. So GT is nothing but a product of velocity gradient into detention time. So there is no unit for this, we will get one number. Velocity gradient into detention time. Velocity gradient unit is 1 by second into seconds. So you will get a dimensionless number only. Detention time also substitute in second, they cancel out. So therefore unitless number will get. So GT value normally ranging from 10 power 4 to 10 power 5 produce larger and large sized dense flock. larger and denser flock, so that which enhances settling very fast. Larger and denser flock. So to get this larger and denser flock, we have to maintain GT value ranging from velocity gradient. If you multiply detention time, we are supposed to get 10 power 4 to 10 power 5. So larger and denser flock means settling velocity of flock depends on size of flock, d square it is, and settling velocity also depends on density of particle. Denser flock you want to get, then you have to maintain that, so that settling velocity fast they settle down. Once they gain enough size and enough mass, they settle down very fast. This is size, this is density. Size of flock, this is density of flock. Size of flock, this is density of flock. Both depend. The settling velocity depends on both of them. Density of flock. So we have to increase size large, density also have to increase. So settling velocity is more, therefore fast it settles down. That is the advantage. So usually we provide tapered flocculation because to have that 10 power 4 to 10 power 5. So we use tapered flocculation. We vary G and T combination. G and T values are varied from inlet to outlet to get larger and large sized dense flock. Okay? So varying G and T values from inlet to outlet is called tapered flocculation. Varying G and T values from inlet to outlet is known as tapered flocculation. We call it as IAS exam sometimes important. Tapering the values, G and T values. Tapered beams, you have heard about tapered beams, no? Cross section changes means tapered beam. So similarly G value, T value changes here from inlet to outlet. Therefore we call it as tapered flocculation. Remember that point, okay? That's it. The design is very simple, same as earlier. Okay? So we divide this into rectangular tank into 2 or 3 compartments. In first compartment, we provide G value very high, and as it go, this is water as water flow from inlet to outlet. So we see that G value keep on changes. In first compartment, we provide G value very high. In second compartment, we provide G value slightly we decrease. Third compartment still we decrease. Like this, 3 or 4 compartments we divide and we vary G and T values. The G value you can vary by adjusting speed of movement. These are paddles. These are called paddles. They will be rotating inside water. So by adjusting the speed, so this will operate at N1 speed. This is operated at N2 speed. This is operated at N3 speed. So where N1 is greater than N2, N2 is greater than N3. So therefore G1, this go with G2, this is G3. Where G1 is greater than G2, G2 is greater than G3. So where G value increases, T value have to decrease to balance it. Here we provide T1, T2, T3. Where T1 is less than T2, T2 is less than T3. So G and T value varying like this is called tapered flocculation. So high G value we provide. G value is very high. So G value ranges from high to low. T value changes from low to high. So as G value increases, T value have to decrease to balance it. So high G value we provide at inlet. Low detention time, short detention time we provide at inlet. So higher G value, short detention time, that produces what happens, smaller and denser flock. This combination produces smaller and denser flock. So as G value keep on decreases, T value keep on increases, therefore size keep on changes. So that's how it happens. Understood? So this much depth, generally they don't ask theory. Okay, anyway, one time in GATE exam they asked that question. So G value is very high and T value is very low. This combination produces smaller and denser flock. Whereas G value is very low, T value is very high, that produces larger and lighter flock. So we don't want to get either of these. We want to get larger and large sized dense flock. Therefore, we need to vary G and T combination from inlet to outlet so that we get larger and denser flock. That is the reason why G and T values varied from inlet to outlet. Understood? Let us try one question example. For that much depth we will not go. Simple questions only will ask. Okay, try this question. Design a flocculator. For a design flow rate of meter cube per hour. Assume detention time of 20 minutes, G 40 second inverse. Also determine the power requirement if mu is equal to 1.0087 into 10 power minus 3 Newton second per meter square. So length to width ratio 2 and depth may be assumed as 0.4 times B. Come on, work out. So design means what? Fixing the dimensions of the flocculator. Come on. Deepam Gupta. Thank you. You are missing me. Okay, we'll meet here. YouTube is there. You can contact me.
Let us try
this question. So what is given to is Q is given 3000 meter cube per hour. Detention time is given as 20 minutes, right? So from this what you can find out? Volume of flocculator, Q into detention time, 3000 meter cube per hour. Convert minutes into hours. So hour get cancelled, left with meter cube. So how much it is? 1000 meter cube, right? And depth is given as, and volume of this rapid mixing unit is a rectangular tank. This volume is equal to length into width into depth. What he has given is length is 2 times width and depth is given as 0.4 times width. So let us work out width. So L into B into H is equal to 1000 we got. So from this you can find out width component. So length is equal to 2 times B, this is B, and 0.4 times B is equal to 1000 meter cube. Therefore B is equal to 1000 by 2 into 0.4 whole power 1 by 3. Cube root it is. Can find out. One 1613.9 watts, Aditya. Thank you, Aditya. So Aditya has given the answer. 16. Okay. First, let us work out B first. 10.7 meters you got. Okay. So length is equal to 2 times B. So 2 into 10.7. It is 21.54, right? .74. This is 1000 by 2 into 0.4 10.77, right? I remember onsets, that's why straight away I wrote. And H is equal to 0.4 times B. 0.4 times 10.77. It is 4.3 meters. So these are the dimensions of the mixing basin, that is flocculator. This is length, width, length, depth. So therefore, length into width into depth is equal to dimensions. So it is 21.54 meters by 10.77 meters by 4.3 meters. Size, rectangular tank we use as a flocculator. Okay, that is first part answer. Design means this is called design. Design is nothing but fixing the dimensions. Second part is power. It is asking power also. Same equation you can use. G is equal to any kind of mixing basin. This equation is same. G is equal to P by V mu. Root of G is equal to root of P by V mu. So G is given as, in the question, he has given G value as 40. Volume is 1000 and mu also given in the question, 1.0087 into 10 power minus 3. And if we simplify, we get power. Power requirement. How much power is required to run that? So 1613.92. watts. So this is how we can work out the questions related to flocculator. Paddle design also there, but paddle design that much depth we will not go. Paddle design means what? So generally size of the paddles. So paddle is rotating inside. This is a flocculator. The bed of a flocculator is a supporting mechanism for paddle. This is a shaft. So this will be rotating. To this we connect, they are called arms. Paddle arms. So to this, at the end you will find wooden plank. The wooden plank is called paddle. This one. This one is called paddle. They are connected back to back usually. Okay. From center of shaft to at paddle tip is this is the radial distance. R. Here we work out velocity at the tip of the paddle. That's called VP. So this is rotating at a speed and RPM. So again omega is equal to 2 pi n by 60. Then velocity at paddle tip is equal to omega into R. So that is 2 pi n by omega into R. If you take velocity at paddle tip will get. But what we use here, power relative velocity will take. So relative velocity is equal to velocity of the difference in velocity between water and paddle tip. This relative velocity we calculate between water and paddle. Between water flow and paddle. Okay, this relative velocity is equal to, so it is Vp minus Vw, velocity of water flow. Okay, that will give VR. That VR we use in the power calculation, that's the only difference. So P is equal to CD AP rho W VR cube by 2. That's how we can work out power. So this AP is equal to projected area of paddles. Projected area of paddles. So paddle has got width the omega B. So it is extended in length direction. Paddle has got like this. This is a paddle. So this is extended along the width of the tank. This is how it appears paddle. This is length of the paddle. This is the length of the paddle. This is width of the paddle. What you can see is width only. This is extended like this in the tank. This paddle is extended along the width of the tank like this. This is the length of the paddle. Just like this. So length of the paddle is what? This is length of the paddle in this direction length. So H is equal to L into B. Projected area of paddle. So how many paddles are there for each shaft? This is shaft. For shaft 2 paddles are there. So how many shafts are there? Number of shafts you have to count. So total projected area of paddles is equal to projected area of paddles is equal to which is equal to the number of shafts into the number of paddles per each shaft so normally 2 paddles or 4 paddles you can use into area of each paddle. Okay, area of each paddle is equal to L into B. So what I drew is that is only this is a paddle section. This is, if you see the plan, this is a tank, this is a shaft. This is a shaft. This will rotate. This will rotate. To this what is connected? Rod is connected. This red color thing is paddle. I'll draw shaft with the black color. This black color thing is shaft. So blue color thing is rotating arm. This arm. To this paddles are connected. This is a paddle. So this is called width of the paddle and this is length of the paddle. So L into B. So that's how it rotates inside the tank. Okay? Paddles will be rotating inside the tank. If you see cross section, it appears like this. If you see the plan, it will be like this. This is a plan. This is section. Okay? I hope it is clear to you. But imagine. That's it, nothing will be there. Then in addition to that, what else is expected? Sedimentation tank. Sedimentation tank designed in the same fashion. Again, no need to discuss. Already we discussed this earlier. Sedimentation tanks are designed based on one surface loading rate or surface overflow rate. Slightly more we provide here. Plain sedimentation tank we provide different values. So to capture this flocculant particle, we provide surface loading rate. It is easy to capture, therefore we can increase surface loading rate. And second is detention time. So using surface loading rate, what you can find out? Surface area of sedimentation tank. But they will give you those values, need not worry. This Q by V naught. So using detention time, what you can find out? Volume of sedimentation tank. So if volume is known, surface area is known, can't you work out remaining dimensions? Comfortably you can work out. Q into detention time. So for rectangular tank, surface area is L into B. For circular tanks, pi by 4 d square. Volume is, for rectangular tank, L into B into H. For circular tanks, it is pi by 4 d square into H. So you can work out rest of the dimensions. So that is not a new thing. Already we are familiar how to work out designs in case of sedimentation tank. How to we can fix up the dimensions of a sedimentation tank. Already we discussed. Let us try one gate question. Simple gate questions they are asking related to only the thing is it's capture flocculant particle. Plain sedimentation tank captures suspended particles. But capturing flocculant particle is much easier than capturing suspended particle. The reason being, flocculant particle keep on changes their size, their mass and their specific gravity. Therefore, the trajectory of the particle movement is non-linear. If you see, the particle is very small by the time it enters the sedimentation tank because of continuous attracting the particles, the neighborhood flocculant particles. So that what happens? Size slowly increases, 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 finally settle down. It enhances the rate of settling. So trajectory of the particle motion is non-linear here. So first if we see this very small particle having very low settling velocity, right, very high flow velocity. But as time progresses, what happens? Particle size keep on changes. So settling velocity also increases. But there is no such thing in case of suspended particles. Suspended particles are discrete particles. No change in settling velocity. Then as some more distance it travel, so it grows into some more size. So settling velocity keep on changes, but flow velocity would remain same. It is a rectangular tank. Okay. So this is called flocculant particle, their size keep on changes. But the trajectory of the particle movement is what? It is non-linear. It is a trajectory. How particles reach bottom of the sedimentation tank. So therefore it doesn't require much force, much effort. The fast they can reach, much faster than suspended particle. They don't require large sized sedimentation tank. Therefore surface loading rate for plain sedimentation tank and sedimentation tank employed to capture flocculant particles. The design parameters if you see, and sedimentation tank which we use to capture floc. So here we provide the V naught value 10 to 20 meter cube per day per meter square. Here you can increase that V naught value to 20 to 30. You need not remember, they will give you these values. And normally detention time we provide here is 4 to 8 hours plain sedimentation time. Whereas detention time we provided in this to capture flocculant particle we don't require that much time, fast they settle down. Sorry. This is advantage of coagulation. So that's how. So size is very small. So small sedimentation tank is sufficient to capture floc. It requires large sedimentation tank to capture suspended particles. Because of those dimensions, it matters. Sorry. Understood? So let us try one GATE question. This question has been asked in GATE exam. So simple and so easy. 2 marks question it is GATE exam. This question is asked in GATE 2014. GATE, not GATE 2012. A town is required to treat for 0.2 meter cube per minute of raw water for a daily domestic supply. Flocculating particles are to be produced by chemical coagulation. Of course, a column analysis indicates indicated that an overflow rate .22 mm per second will produce satisfactory particle removal in settling basin. Question is much length, but answer is only one line. At a depth 3.5 meters. The required surface area of is given in meter square for settling is. This question is asked in GATE exam for 2 marks. GATE 2012. Come on, work out all of you. So simple and so easy. If you give me the question, I can solve. Aditya, if the question is there, I can help you. Test series prepared by people, so just to create a new question, so they take some strange data, make your life difficult. So that is not a proper way of framing the questions. Scientifically they have to frame the questions. Scientifically they frame, easily you can solve. Just to make your life difficult, some data purposefully they don't mention there. If you wish, you can note down Arjun, no problem. Note down Arjun, are they useful to you? So I am not giving complete details, but in brief. Because whatever you require to solve the problem, whatever support you require to solve the problem, that much I am discussing in the class.
Okay, let us solve.
So what is there? Only one line answer it is. This much big question is there, but answer is only one line. So Q is given. What is required to find surface area? Q is required. That is given. Then what else is required? V naught is required. So V naught is given in velocity units. No problem. No issue. That's it. So surface area is equal to, it is Q by V naught. Q given in the question is 4.2 meter cube per minute. Surface loading rate is given as surface overflow rate 0.2 mm per second. So surface area in meter square you have been asked to find out. So Q by V naught. So 4.2 by 0.2. So this is meter cube per minute. I am converting this into meter cube per second. Okay. Let me convert this into meter cube per second. This V naught 0.2 mm per second. Let me convert this into meters per second. So meter cube per second by meters per second. This will give answer in meter square. Can work out now? Working out along with you. So I got 350 square meter. This is 2 marks question. Anything is there? Any difficulty is there in answering this question? Nothing is there. Straight to 2 marks questions. These are so simple and so easy. This kind of questions only they will ask. That's why previous year questions are very, very important. So don't, if you feel difficulty in solving test series questions, don't worry. Because they are prepared by people like us only to make your life difficult. So that you will be cautious, you will not take the things for granted. So, maybe difficult to you, test series, no problem. Test series, you can perform much better than test series in the actual exam. Okay? Don't worry, because in actual exam you don't find any redundancy in the question. You don't find any redundant information in the question, you will find crystal clear information. With crystal clear concept you can answer. Okay? That much I can assure you. Test series, because people to create innovative questions, so they purposefully keep some redundancy in the questions and make your life difficult, and they try to scare you. Okay, don't worry about test series. Take test series, that's good, But don't worry about the questions in test series and all. You try to solve as much as you can. But don't worry about the performance in the test series. Okay? Simple questions you find difficult to solve, then something wrong with your preparation. Tough questions are redundancy is there in the question, that is tough to everybody also. The person who created that question also he cannot solve properly. Don't worry about that. Okay? So finally we have got Clariflocculator. So it appear like this, Clariflocculator. This is a rapid mixing unit followed by flocculator followed by sedimentation tank. So it appear like this. Cross section of Clariflocculator, you see, it will be like this. Rapid mixing unit, so something will be rotating here. So water will be moving from rapid mixing unit to flocculator. Flocculator, paddles we provide here, paddles will be rotating inside. These are the paddles. So water will be moving from this unit to that unit serially, one after the other. Then water get into sedimentation tank. There, this flock will settle down, and finally the clarified water reaches there. So all the flocks settle at bottom as a sludge. So once flock settle as a sludge, that remain here only. Only water flow into outlet. From there we can collect, take water to next level of treatment. Here flow in, here flow out. This is cross section of Clariflocculator. That is how it appears. Understood now? That's all. So without wasting time, let us see the filtration process also. Let us continue our discussion with the next topic, filtration. Yes, coagulation, flocculation, sedimentation, all of them occur in a single tank. That's called Clariflocculator. This one is 1, this is 2, this is 3. One is rapid mixing unit, two is flocculator, and 3 is sedimentation tank. So all will happen in single unit. Understood? Arjun, is it clear now, Arjun, to you? Is it clear to you, Arjun? Okay then, let us go ahead with the next topic, filtration, without wasting time. So, coagulation aim to capture colloids. Sedimentation, plain sedimentation aim to remove suspended particles. Next is dissolved particles. The dissolved particles present in water and as well as pathogens we need to remove from water so that it become complete wholesome. So to capture those dissolved particles and as well as the flock which escape from sedimentation added to coagulation, we employ filtration. Filtration is nothing but passing water through a stationary bed of granular media. So passing water through a stationary bed of granular media is known as filtration. This granular media which we use to carry out filtration is known as filter media. So granular media such as silica sand, anthracite coal, Of course, except sand remaining are not available in India. So in general, filtration is means it's only sand, anthracite coal and garnet are used. Garnet is nothing but a green sand used as filter media. They are known as filter media. So in India it is only sand. You don't find anything beyond sand. So whenever we talk about filter media, by default it is only sand, granular media. So passing water through a bed of sand is called filtration. So sand bed is packed at one place. This is filter media. This is sand bed or filter media. Granular media, okay, for which we apply water. On the top of it we apply water. So water passes through this granular media. I'll show water with red ink. Okay, sand with red, water with blue I'll show. This is sand bed. This is only taken as filter media. On the top of which we apply water. So water move from top to bottom. While it is passing through sand bed, all of the impurities present in water, they are captured by sand. So you will get impurity free water. So before passing through this sand, concentration of impurities are C0. After passing through sand bed, concentration of impurities are Ct. This Z is called thickness of filter media. So when water passes through jet thick sand bed, so concentration of impurities are removed from C0 to Ct. So change in concentration is C0 to Ct. This process is called filtration. Understood? So I got so many types of filters, right? Filters are classified based on several criteria, but among them three are important for exam point of view. One is slow sand filter. Slow sand filter. And second one is rapid sand filter. These two are very important for exam point of view. And third one is pressure filter. So these two are very popular. In bulk water treatment, rapid sand filter, slow sand filter are very popular. You have to learn how to design them. Understood? Am I confusing you? Am I going fast? Gravity filters, pressure filters, that and all classification is there. But that much clarity, that much detailing is not required in this revision class. So that's why I am writing simply slow sand filter, rapid sand filter, pressure filter. Let us see about slow sand filter. Slow sand filter is single media, gravity type slow filter. It is a single media type, only sand is used as a media. It is a single media, only one media is used. Some filters 2 media, 3 media also they use. They are multimedia, double media filters. This is single media, gravity type, slow filters. Why they are called slow filters? Because the rate of filtration is very low. Known as slow filter. Slow filter rate of filtration is very low. So slow filter we call rate of filtration. The shortcut to rate ROF is very low. Rate of filtration means rate of filtration, or people also call it as loading rate. It is some design parameter actually. It is volume of water passes through media in a given time per unit surface area of filter. Volume of water filtered in a given time per unit surface area of filter is known as rate of filtration or loading rate. The rate of filtration is shortcut to rate ROF, or the other name of this is loading rate. This is very less in case of slow sand filter. For slow sand filters, rate of filtration is normally it is 100 to 200 liters per hour per meter square. That means if you wait for 1 hour, if you apply 1 square meter filter media, then how much water you get? 100 to 200 liters only. Very low. That's why they are called slow filters. But the job it performs is extraordinary job it performs. Right. Rate of filter. I am talking about slow sand filter only. It is 100 to 200 liters per hour per meter square. We express like that. Volume of water filtered in a given time per unit surface area. It is very low. Whereas particle removal efficiency is very high. Particle removal efficiency of slow sand filter. No one can match with slow sand filter in terms of removing impurities. It is 98% to 99%. So almost it produces absolute purity water. Almost 98 to 99% impurities in water are removed by slow sand filter. Now how it works, how it is cleaned, this and all not required for GATE exam. Normally slow sand filters are operated till it reaches to the final head loss 90% of the thickness of the sand bed. Slow sand filters operated till filter reaches to final head loss 90% of thickness of filter bed. So that means it is 70 to 90 centimeters of water in case of slow sand filter, because the thickness of slow sand filter, let us assume thickness of this one only, thickness means this one. This is thickness of filter bed or sand bed otherwise. Thickness of sand bed it is. Normally for slow sand filter it is 0.9 to 1.1 meter. So 90% of that value means usually it is so 70 to 90 centimeter. Till it reaches to 70 to 90 centimeter, you can operate. 90 to 110 centimeter otherwise.
Head is
expressed. Head loss. H is equal to P by gamma. Pressure head it is. So head is expressed in terms of meters or centimeter. Understood now? Fluid mechanics studied, completed that course, isn't it? So these are some of the information very useful while designing the filters. So based on final head loss, sluice and filters are cleaned or washed. So frequency cleaning of sluice and filter is done by scraping. Cleaning of all these points, important some theory questions also they are asking. Is by scraping. Scraping top 1.5 to 3 centimeter layer of sand. So that's how sluice and filters are cleaned. So frequency of cleaning sluice and filter is once in every 1 month to 3 months. Cleaning or washing. Sluice and filter is once in every 1 month to 3 months. So all these points you keep in your mind. They are asking in exam. Okay. So I'll teach you straight away designs, how to solve numericals. So this information is more than sufficient to work out numericals. Boss Khan, so serious. What I can do, I can't see you, no, to make fun of you. I can't see nobody, I can see only camera. So if I see the students, at least I can make fun of them. Some jokes we can cut. Okay, I'll start geotechnical also. So January, I'll start geotechnical. Planning to start geotechnical also. We'll revise geotechnical also, no problem. So 1 or 2 times you write formula, then you can remember, Arjun. Not so difficult it is. Practice, you have to practice. Make a small, whichever formula you are forgetting more, you write a couple of times, you can remember better. See the parameters in that formula, what is the variable, what are the constants. If you look at the formula if you pay attention, 3-4 minutes towards formula and see what are the quantities in that formula, which is a variable, which is a constant. Pay a little attention, you get more idea. You can learn the subject also with formula. Okay. Thank you, Abbas Khan. Okay, then let us see the design part of filters. Any filter is designed. You saw me teaching this subject only, right? That's why we are saying like that. Design of sluice and filter. There are 2 ways we can design. Type 1 is, okay, first common we work out total surface area of sluice and filter required. by rate of filtration. Once you find out this, there are two ways you can design. The method one is fix size of number of filters, find size of each filter.
Because
One filter of that much surface area you can't provide, then in this case you can have multiple number of filters. Find the size of each filter. Size of each filter means what? Finding length of the filter and width of the filter. So how you can do it? So once you fix the number of filters, so area of each filter is equal to, it is L into B, which is equal to total surface area of filter required by number of filters. Total surface area already we got here. Okay? Then L is to B ratio will be given. So from L is to B ratio you can find out length of the filter and as well as width of the filter. That's first way you can work out. So provide one or two extra filter as a standby. And method 2. So simple, so easy. Fix size of each filter. L and B. Then find number of filters. Size of each filter is known, you can find out area of each filter then. So number of filters N is equal to total surface area of slow sand filter required by area of each filter. The area of each filter L into B. Area of each filter is equal to surface area only, L into B. That's all. We don't have anything to work out. But the thing which you need to remember is we provide one or two filters extra as a standby units. If they mention in the question, we provide. Otherwise, we ignore. Normally, in practice, we provide standby. But in the exam they give you, then only we provide. Otherwise, we ignore. One or two filters extra provided as standby filters. Okay? Like Indian cricket team is there, 11 players only sufficient to play, but how many they select? 13 players they select. Why 13 players they select? So any player get injured, then immediately they can employ standby player. Exactly how standby player is useful, bench player, bench, reserve players. Same way, any filter give trouble to you, immediately the standby filter put into operation. Therefore, so total number of filters provided is equal to total number of filters provided is equal to N plus number of standby filters. So N is equal to number of filters in operation. So always N number of filters should be in operation. So standby filters normally we keep them idle. In emergency only we put them into use. Any of the filter troubles you, give trouble to you. In emergency we use standby filters. Understood?
Okay?
Let us try one question.
Example. Find how many number of
Slows and filters of size 20 meters by 10 meters required to treat 10 ml of water with a rate of filtration 200 liters per hour per meter square. Come on, try.
this kind of questions
Only they'll ask 1 mark, 2 marks. So you can't expect beyond this. Okay? So what is given to you? Q is given. The size of each filter is given. On the size of each filter, L into B is given. And rate of filtration is given to you. The first step, what is that? Total surface area of slow and filter required is equal to Q by rate of filtration. This Q is given million liters. Million liters to convert into liters, 10 power 6 liters per day. To convert this into liters per hour by 24. Then it becomes liters per hour by 200. 200 also liters per hour per meter square. So liters per hour, liters per cancel, you get with the meter square answer.
On how much
This is
So it
It's 2083.33 meters square you got. But area of each filter, how much? Area of each filter, dimensions are given. It is 20 by 10, so it is 200 meters square. Therefore, number of filters required is equal to total surface area by area of each filter. So come on, work out. So it is 2083.33 by 200. It is 10.41. So 10.41 you can not provide. So it is 11 filters. So nothing mentioned regarding standby, ignore. GATE exam now it is. So absolute data is given to you. With that data you have to work out. If they mention any standby unit, including standby how many requirements, including one standby how many requirements, 11 plus 1, 12. Including two standby how many requirements, 11 plus 2, 13. Something like that we work out. Okay? Let us try one more question because so much time is there. So design 6 slow sand filters are given data. For the following data otherwise.
population
Is equal to
50,000. Per capita water demand is given as
so long time we got this data. 150 LPCD. Rate of filtration is given as 180 liters per hour per meter square. Length is equal to 2 times B. And maximum demand is equal to 1.8 times average demand. Assume 1 unit out of Assume 1 unit out of 6 as standby. Okay? So how many you have to design? Only 5. How many required? 6 required, but 1 is kept as a standby. So number of filters in operation is equal to that only you have to take into account. So number of filters provided minus number of standby units, that is 5. So Q value is given as not given, indirectly given, population is given, and per capita water demand is given. Population into per capita water demand always give Q value. How much water is required? So it is 50,000 into per capita water demand is given as 150 LPCD. So you will get liters per day. But I have been asked to design for maximum demand. But Q max is given as 1.8 times Q. That is also given to you. Therefore 1.8 times 50,000 into 150 liters per day. Okay, this is Q max. So using this Q max we work out total surface area of slow sand filter. Total surface area of Because he has given Qmax, we are using. Otherwise, we would have taken only Q into account. Slow sand filter required is equal to. So in this case, Qmax by rate of filtration. We don't assume anything in exam, competitive exams. Whatever data is given, for that data we work out. Because he mentioned Qmax, so we are designing for Qmax. That is correct only. So which is equal to 1.8 times 50,000 into 150 by 24. Converted this into liters per hour, and this is 180. This is also given in liters per hour per meter square. Therefore, they cancel out, we get answer in meter square. Work out. So it is 1.8 into 50,000 into 150 by 24 by 180. So it is 3125 meters square. So area of each filter is equal to this L into B. It is equal to total surface area of filter required is total surface area by number of filters in operation. So 3125 by 5. 5 only we design. 6 we will provide, but we design only 5. Because one filter acts as a standby. So it is 625 meters square. Cell is given as 2 times B. Therefore, 2B into B is equal to 625 meters square. From this you can calculate B value. 625 by 2 under root. So it is 17.67. That's all. Problem is over. So length is equal to 2 times B into 2. 35.35. Therefore, provide 6 filters. Each of size 35.35 meters by 17.61 meters, out of which one filter acts as a standby. So how many filters are in operation? Only 5 are in operation. So that is how we work out the questions. Okay. So Unacademy conducting so many mock exams. You can enroll for those exams. You can use GATE Civil code. You get 10% discount using this code. So many subscriptions are there. Again, I'll be taking tomorrow morning 9 o'clock to 11 o'clock. I'll take class tomorrow. Tomorrow also I'll take 2 sessions. Morning 9 to 11 one session, and afternoon 8 to 10 one session I'll take. Okay, tomorrow I'll complete mostly water treatment will be over by tomorrow. Then we'll start where we'll complete water supply engineering. Little promotional content is there, just go through this. You can avail. Your code you can use is GATE Civil. Okay, then I'll stop here today. Thank you. Again, we'll meet tomorrow morning 9 o'clock. So attend the classes, may be useful to you.